Welcome to The Explainer. Today, we're going to dive into one of the most beautiful ideas in all of science, how our universe, from the weather to life itself, manages to create breathtaking complexity out of the absolute simplest rules.
For centuries, this was the big dream of science, this idea of a clockwork universe, first imagined by guys like Newton. This quote from Laplace sums it up perfectly. The thought was, if you could just know the location and speed of every single particle in the universe, you could predict the future with 100% certainty, like a perfect cosmic machine.
But of course, we all know reality doesn't really work that way, right? We live in a world that's full of surprises. A world where even our most powerful supercomputers still get the 5-day forecast wrong. The reason for this isn't some failure of science. It's actually a really profound discovery about how the universe truly operates. And the answer is chaos.
Okay, so first up, we're going to see how one really simple ingredient, something called feedback, can take a perfectly orderly system and turn it into something completely, utterly unpredictable. So the old way of thinking was pretty straightforward. Simple rules lead to simple, predictable results. But then, the study of chaos just completely flipped that on its head. It showed us something kind of mind-bending. You can have a system with simple rules that are perfectly deterministic, meaning there's zero randomness involved, and yet it can still produce outcomes that are fundamentally impossible to predict over time.
This is the famous butterfly effect, and believe it or not, it was discovered completely by accident back in the 1960s. A meteorologist named Edward Lorenz was running a weather simulation. To save a little time, he re-entered a number from a previous run, but he rounded it off, from 6 decimal places down to just 3. And that tiny, seemingly meaningless change produced a completely different weather forecast. It's where we get the idea that a butterfly flapping its wings in Brazil really could set off a tornado in Texas.
Okay, now take a look at this equation. It looks so simple, right? Almost harmless. It was originally designed to model something as basic as population growth. But as we're about to see, it's actually a perfect recipe for chaos.
This is where the magic really happens. You create this feedback loop. You take the output and you feed it right back in as the new input, over and over again. And depending on the value of that b variable, the system's behavior just transforms. It might settle down to a single stable number, or it might start bouncing between 2 numbers, then 4, then 8, in this cascade of splits, until finally it just collapses into complete, patternless, unpredictable chaos. All from that one simple equation.
So, if chaos isn't just a jumbled mess of random noise, what does it actually look like? Well, it turns out chaos has this incredibly beautiful and intricate geometry.
The visual language of chaos is the fractal. Fractals are these infinitely complex patterns that look the same no matter how far you zoom in. Think about it. You zoom in on one tiny piece and boom, you see the whole picture again, just smaller. An endless repeating complexity.
And what's just mind-blowing is that these aren't just some abstract math concept. They are everywhere. Nature uses this exact same chaotic fractal logic to build the world around us. You see it in the way lightning forks across the sky, or how the branches of a tree reach for the sun, or even how our own lungs branch out to absorb oxygen.
So what's with this weird number, 1.25? Well, that's the approximate fractal dimension of a typical coastline. Now, we're used to whole numbers for dimensions, right? A line is 1D, a square is 2D. But a fractal shape is so wrinkly and complex that it actually exists between dimensions. It's more than a simple line, but it doesn't quite fill up a 2-dimensional surface.
And this leads to a really famous and kind of brain-twisting question. So, how long is the coast of Britain? And the shocking answer is, it totally depends on what you use to measure it. If you use a giant 100-kilometer ruler, you get one answer. But if you use a tiny 1-meter ruler, you can measure all the little nooks and crannies, and your total length will be way, way longer. The smaller your ruler gets, the longer the coastline becomes, literally stretching out towards infinity.
Okay, so let's take these ideas now from these static shapes and see how they apply to dynamic, evolving systems. Systems that are constantly teetering right on the very edge of chaos.
This is the idea of self-organized criticality. And the best way to picture it is to think of a sand pile. You add grains of sand one by one, the pile gets steeper and steeper until it reaches this critical state. And at that exact point, the very next grain of sand could cause a tiny little trickle, or it could trigger a massive catastrophic avalanche, and you have no way of knowing which it will be. The system naturally drives itself to that perfect, unpredictable tipping point.
And this is exactly what happens with the Earth's crust. It's another system that's always in a state of self-organized criticality. Stress builds up along fault lines, and then it's released in earthquakes.
The Gutenberg-Richter law here shows us a clear pattern. Small earthquakes are incredibly common, while the huge catastrophic ones are extremely rare. And they follow this very specific statistical pattern called a power law.
And here's the kicker. This pattern isn't just for earthquakes. Not even close. The exact same signature, sometimes called 1F noise, shows up in stock market crashes, the size of forest fires, how traffic jams appear out of nowhere, and even in mass extinctions. It's like a universal fingerprint for all kinds of complex systems that are poised right at the edge of chaos.
All right, now let's zoom all the way out and apply these big ideas of feedback and self-organization to the biggest system we know, our entire planet.
Back in the 1960s, a scientist named James Lovelock was working with NASA on a huge question. How would we find life on Mars? And he had this brilliant realization. You don't look for little green men. You look at the planet's whole atmosphere. A dead planet, like Mars, has a boring, stable atmosphere. It's in chemical equilibrium. But Earth's atmosphere, it's a raging chemical fire, just full of highly reactive gases like oxygen that really shouldn't be there. Something has to be constantly pumping it out. And that something is life.
This incredible insight led Lovelock to propose the Gaia hypothesis. The idea here is that life isn't just some passive passenger on Earth. It actively creates and maintains the conditions for its own survival. The whole system, the biosphere, the atmosphere, the oceans, they all work together in this vast, self-regulating feedback system, almost like a single giant living organism.
And this is just brilliantly shown in a simple little computer model called Daisyworld. So imagine a planet with only two life forms, black daisies and white daisies. When the planet's sun is cool, the black daisies, which are great at absorbing heat, they thrive, they spread, and they warm the planet up. But as the sun gets hotter over billions of years, the white daisies, which reflect heat, get the advantage. They spread and cool the planet down. This simple feedback loop keeps the planet's temperature perfectly stable for life, without anyone or anything being in charge. So, where do we go from here? Well, we take this profound insight, and we point it to the stars, in the search for other living worlds.
You see, the modern search for alien life isn't really about listening for radio signals anymore. It's about searching for other Gaias, other planets where life has completely taken over the world's chemistry and thrown its atmosphere into that same state of wild disequilibrium we see here on Earth.
So how do we do it? Well, the plan is to use these incredibly powerful space telescopes to look at the light from distant exoplanets. As that light passes through their atmosphere, different gases leave a unique chemical fingerprint. And the gold standard we're looking for isn't just oxygen, it's ozone. If we find a thick ozone layer, that implies an atmosphere that's just loaded with free oxygen, a gas so reactive it would vanish in a cosmic heartbeat unless something, a global biosphere, was constantly churning it out.
So from a simple little equation that just explodes into infinite complexity, all the way to a global ecosystem that regulates itself, what this science of chaos really shows us is a deeper truth. The universe isn't some dead, predictable clock. It's a dynamic, creative, self-organizing system. And finding another living world out there, that would be the ultimate proof that we are not some cosmic accident, but a natural expression of a universe that is just poised to create order out of chaos.